Uh, okay, go ahead, Mumi.
Yes, sir. So today I'll do this paper presentation on this particular topic: machine learning deciphers CO2 sequestration and subsurface flow path from stream chemistry. So this work is a PhD work by Andrew R. Shoginsky, and he is currently a PhD student in Pennsylvania State University at USA. So the importance of carbon sequestration is already known, because normally the carbon dioxide balance is maintained by two opposite processes. So one is the carbon dioxide is released from the earth to the atmosphere by volcanic degassing, whereas by the different weathering processes, it is again the carbon dioxide is sequestrated in the earth surface. However, currently in current scenario, due to the burning of the fossil fuels, large amount of carbon dioxides are released, and these carbon dioxide have been sequestered for long, and this upsets the already existing balance. So it is very essential to understand the whole system and how the processes are changing. It is important to understand what is the balance between the different weather, like how the weathering mechanism, how it changes the amount of carbon sequestration. So in generally, chemical weathering is common, and these are the various reactions how carbon dioxide sequestration occurs. So normally any model, they take into consideration the weathering of silicates and carbonates that is mainly conducted by carbon dioxide CO2 weathering. However, the another component which is often ignored is the weathering that occurs by pyrite or the sulfuric acid. So the acid rain that would cause this H2SO4 weathering. However, within the surface, like at particular depth, a large amount of pyrite is also present, and this pyrite oxidation that would also it will also cause the weathering processes, and that will also change uh, the amount of carbon dioxide that is sequestrated. So if we see that during the weathering of silicates by carbon dioxide, when the dissolution of the silicate occurs, so in that case, 2 mole of carbon dioxide is removed from the atmosphere. However, again, during the marine carbonate precipitation, we lose 1 mole of carbon dioxide, like 1 mole is released into the atmosphere again, and only 1 mole of carbon dioxide is sequestrated. In case of carbonate, this net amount of carbon dioxide lost is 0. And in case of silicate weathering by H2SO4, this net loss of carbon dioxide is 0 from the atmosphere. And if H2SO4 weathering occurs on carbonate, instead we are gaining half carbon dioxide, and I mean this carbon dioxide is released into atmosphere. So most of the models, they do not take into consideration this addition of carbon dioxide into the atmosphere. So in this paper, what they have done is they have considered this H2SO4 weathering as well. So for this purpose, they have studied 3 well-studied watersheds. So one is the Shale Hills, which is a acid rain impacted watershed. The second one is the East River one, which is shale hosted, but it receives very less amount of acid rain. The Hubbard Brook one is extensively impacted by acid rain, but it is in these two cases, there was only a single lithology unit, but here different schist and glacial till, so different kind of bedrocks are present in this case. So machine learning model have been used to build a model so that they can predict the end member of the stream water. So in normal end member mixing analysis, or EMA, which is commonly used by the people of groundwater chemistry. So in this model, what the inputs are the assumed end member chemistry and the measured stream sample chemistry. So these two are the inputs, and in the model, this is an inversion model. So in this model, the ultimate output is the mixing proportion. So for example, how much mixing of different sulfate sources have occurred, from which depth of like if it is a up if the flow of water is from the upper level, or it has occurred by reaction at a very higher depth or greater depth. So these proportions are found as an output. However, the problem of this model is that in recent many of the analysis, what they have found is unrealistic contribution of acid rain or models are predicted, and the models, they do not converge in many cases. Also, we need to assign up like before the starting of the model, before applying the model, we need to assign the accurate end member chemistries because it occurs as an input. However, in case of the machine learning model, the derived end member chemistry, we do not have to assume it, and it is coming as an output. So that is a benefit of this model. Also, so in this particular machine learning model, only the input is the measured stream sample chemistry. So this is already measured, so we do not have to make any other assumption. By applying the PCA, what they try to find out that how many end member compositions are there. So, according to that, 2, 3 end member compositions are assigned. And after that, this NMF algorithm is applied. So here it is like first boots because the sample or the training data are often less in number. So first a bootstrapping is done to increase the data volume, and then blind source separation is done. And NMF is one form of blind source separation. And from that, we get these outputs. Like first is the derived end member chemistry and the mixing proportion, in which proportion they are mixed. So for this, in this particular paper, what they have done is they have built a synthetic data model based on this equation V equals to WH. So V is the measured stream sample chemistry, and W and H are the two factors that have been like that have been used. So NMF is a common model, which is a blind source separation model. It is a very common model and have been applied in various other cases. But for like stream chemistry analysis, it has only been used recently, and this paper reference has been given. So using this particular model, they have shown that these are the predictions or these are the output. So what they can see is that this is the model mixing proportion and these are the true mixing proportions. So they have used the synthetic data, and we can see that the predictions, they are almost matching, like they fall on the same line. And in case of true end member chemistry as well, the fitting is very well. And as we can see that the R-square value is 0.98, and in this case, it is almost 0.99. So after they have established that this model works, so they have tried to apply it on these 3 well-studied watershed. So before applying them, what they have taken into consideration is the lithology of the area. What are the parameters we already have, or what are the constraints that have already been placed on that particular watershed by the previous studies, etc. So for that purpose, so they have taken this schematic cross section of shale hills to understand the lithology of the area. So as we can see here, this is the cross section, and how is the chemistry of the area? So the pyrite and carbonate, they are not found on the surface of the watershed. Instead, they are found at quite a depth. And elite is the mineral that is found on the surface, whereas chlorite is commonly found in the whole lithology. So this kind of like these layering of the lithology, that will impact the weathering and how the interflow, that is the flow on the upper surface, whereas the groundwater flow, how both of them will influence the ultimate stream water chemistry, because the acid rain, they'll be only be influencing the interflow water, how they'll not percolate into the groundwater flow in most cases. In some cases they might, but mostly they are restricted to the interflow. And the groundwater flow, they'll be more related with the deep weathering, and they'll weather or mix with the carbonate or pyrite type of chemistry. So these are the chemical compositions that have been measured. So I had mentioned that PCA is done earlier. At the first step, PCA is done to understand how many N members are present. So in case of Shell Hills, they have found that there are 2 N members, the shallow and the deep one. And in the East River also, they have found 2 N members. Whereas at Hubbard Brook, they have found 3 N members. So they have categorized it in this way. Also, one major important thing is on the surface, because elite is being weathered by the interflow at the surface. So if we see that the magnesium composition, they are higher at the shallow. So the chlorine composition, which is indicative of the acid rain, so that is very dominant at the shallow depth. As we see at a deeper level, the chlorine concentration is very low. So at the surface, by the interflow, the chlorine concentration is high, whereas at the depth where the carbonates are present, so their concentration is high at a deeper level. So what they have seen is, also they have studied the DEL sulfur isotope to understand if their particular model, they fit with the sulfur isotope chemistry or not. So according to this particular model, at Shale Hill, what they have predicted is, at shallow depth, the carbonate is absent and silicate weathering is more common, and acid rain weathering can cause, like acid water, they can cause weathering by H2SO4 during the wet season. So what they have found is, during the wet season, the influence of acid rain is more, and therefore, and because carbonate is absent at shallow depth, so most weathering is occurring by the silicate, most weathering of silicate minerals are occurring, and therefore, during the wet season, the basin that acts as a source, that is more carbon dioxide, is released into the atmosphere during the rainy season. Whereas during the dry season, the water table is dropping and only the pyrite oxidation occurs that can supply the H2SO4. And however, at a shallow depth, because of the normal water flow, the carbon dioxide weathering of the silicate occurs. So therefore, in a during the dry season, this basin, they act as a sink of carbon dioxide. That is, it is actually the carbon sequestration is happening. So already earlier studies, they have predicted that 44 millimole per meter square per year carbon dioxide drawdown occurs by silicate weathering. So applying their particular model as well, what they have found is, if only silicate weathering by CO2 is considered, almost 38 millimole per meter square per year, based on this machine learning model, can be predicted. So these two values are very close. However, because only carbon dioxide driven weathering is being considered, therefore this is an overestimation, because we have already seen that in case of sulfate, weathering by sulfuric acid, instead the carbon dioxide is released into the atmosphere. So no, as I mentioned, that sulfur isotope is also considered to cross-validate what they have found. So what they see is that these are the sulfuric acid, like the sulfur isotope values. And if we consider the acid rain isotope value, so that is about +5 to +3. So this value matches with most of the composition and most of the shallow water values. So at the shallow level, so the influence of acid rain is very evident here, whereas these values gradually become lighter as we move towards the influence of the deep water, and they are moving towards the sulfur signature, 34 sulfur signature by pyrite, which is about -20 per mil. So del 34S sulfur of pyrite is minus 24 per mil, and that means that the contribution of pyrite dissolution is affecting the samples where there is more contribution of a deep weathering. So also what from the literature data, they have collected the sulfur flux over the year, and this is the particular curve that they have found from the literature data. And from the NMF derived flux of sulfate from rain, this is the range. So what they observe is there is a certain deviation, as we can see, and instead this value matches with the sulfur concentration or the sulfate flux at there is a time lag, or as it has been calculated, there is a 19-year time lag. So this is the rainwater composition, whereas this is the stream water composition. So what they have predicted is that between the rainwater and the stream water composition, there is a 19-year lag. So the composition of the rainwater, because it takes time to percolate and mix with the stream water. So finally, the lag is about 19 years. So they have predicted 19 to 34 year lag. So based on the shale hill chemistry, so they have also tried to predict the East River and the Hubbard Brook chemistry. So as we can see that here the K stream is calculated. So if the value is towards negative, that means that the stream, the basin is acting as a sink. That is, the carbon sequestration is happening. Whereas if the value is positive, that means that carbon dioxide is released into the atmosphere. So as we can see, during the dry season, the values are getting low, and during the wet season, the values are increasing in case of shale hills. So this indicates that carbon sequestration is mainly occurring during the dry season, as they have predicted from the model. And this is the output. So, however, if we look at if the same model is applied at East River, the opposite thing, like the exact opposite observation is made. That is influence of acid, because here the influence of acid rain is very minimum. Instead, glacial meltwater is influencing the system more. Therefore, during the melting season, the system is acting as a sink, because the surface weathering is occurring and there is very less influx of the sulfuric acid. Instead, CO2 weathering is occurring, and therefore it is acting as a sink during the snow melt season, whereas during the dry season it is acting as a source. So as here we can see, if we come to this image again, so what we can see is during the snow melt season, the values are decreasing, whereas in the base flow the values are increasing. So during the snow melting season, the values are decreasing compared to as the base flow season, which is opposite to that of the shale hill. So they have also tried to predict this on the Hubbard Brook area. So here, as I had already mentioned, that they have the bedrock differs from one level to another. So here, what they have observed, like earlier studies in BioLink 2020 or the previous, many of the studies, what they have predicted is the concentration of sulfate in acid rain that has declined over the time in northeastern USA. So at Hubbard Brook, as already mentioned, there are 3 N members. So of those 3 N member composition, 2 of them, they show a declining sulfate concentration with time. So therefore these 2 N members, they have been contributed to the acid rain, whereas the third N member that does not change with time is attributed to the deep weathering in water, and that is that which is interacting with the underlying bedrock. So here, as this composition, this is decreasing with time, and it has been said that this major composition is rain derived, and that is contributing to the change with time, whereas the sulfate derived one is constant over time. So the deep water, that is constant over time, whereas the other 2 N members, they are gradually decreasing. So So ultimately, what they have concluded is the Shale Hill and the East River net, they are acting as net neutral with respect to CO2, and whereas in case of Hubbard Brook, it is a net sink. So over time, only it is acting, helping in the carbon dioxide sequestration. However, if only the CO2 weathering was considered, the amount of drawdown of CO2 that would be overestimated. So they apart from predicting from the stream water, what they tried to do is also they tried to predict the same from the rock chemistry. So this is to cross validate. So what they have found is at Shale Hill, from stream water, they have predicted a slight almost neutral value, and from rock also these two values are close to zero. At East River also the values are close to zero, whereas at Hubbard Brook they have found that there is a net negative value, which means that carbon dioxide is sequestration is occurring at Hubbard Brook area, whereas in these two cases the net value is zero. And this is predicted from both the stream composition as well as the rock composition. So what they have said is they have stated as the impact of the work is that they can successfully reproduce the source proportions, and it is a better prediction than the existing models where the n members are already they have to assign the n member composition. So their study has also revealed some new information how the watershed works, and they can be applied to new studies. So they had already mentioned earlier in their paper that the source appointment of stream with time, the variation with time can also be calculated, and their work will help in constraining the global weathering related carbon dioxide CO2 dynamics, because it can delineate n members without any prior assumptions. So these are the impact of the studies that they have mentioned, and that is all. So.
Okay, thank you, Wumi, for first leading the discussion. Let us go through this paper. I think for the rest time, we are going to do some discussion. Yeah, feel free to open your mic if you have a question. Actually, I have some comments to start with, and actually the last comment is a question to begin with. So to point out that because, yeah, the people that discussing today, most of them are working my group, and also we have Scott Hansen, who's a hydrogeologist. And probably Scott later on could make more comments, but I would like to start with is that first the fluid chemistry that people describe here are mainly about the cations, anions, which in the inorganic chemistry like mineral rocks that we mainly analyze are the oxide concentrations. So for this. For water that people really care about pH. Actually, it's interesting that at the more extreme temperature and pressure conditions, pH as well as the cation anion reactions in equilibrium are very different than what happens at the 1 atmosphere. For example, if you go to 1 GPa in Earth's mantle, the neutral water, which is supposed to be neutral, the pH is not 7. I do not remember the exact value, but it's not 7, it's like 5 or 6 because the equilibrium conditions are different. This is one point I'd like to make. And the second is that while it's really great that for hydrogeologists have so much data because their time series is just amazing. You could just have every week's data. Where for geologists, we count in million year scale, whether we have the data throughout Earth history. And last question is a comment about the question. So here is they describe it, but I still do not know the details of how that they can make this n member calculation by machine learning without a prior assumption. I think this part is really useful because for what the Chuntao is working now, I think I don't know whether it's applicable. Maybe Wumi could go explain a little bit, and then Chuntao could make some further comments on it. And then, of course, Scott is welcome to jump in at any point.
So this method is a part of the blind source separation method, which is already used in different studies. So they are used for in sound systems as well, or different signal processing. This blind source separation is already used. So if I look at the paper, they have mentioned it there. So in the supplementary as well, they had mentioned that in detail. So if I look at the paper, what they have done is this. They have taken this matrix. So V is equal to WH, and in this V is a matrix that consists of N and M. So N is the tempo, like the N refers to sampling date, and M refers to different solutes. So the different compositions, Ca plus, Mg2 plus. So this is the matrix V, and this W and H. So W is N into P matrix, where N is the same one, that is the sampling date, whereas P refers to the number of sources. So possibly this P they have derived from doing the PCA. So how many N members are possibly they are explains 90% of the variation. So more than 90% of the variation. So that is the P. So here, for example, in first two cases, what they found that the N member composition are 2, and in the third case, they have found that there are 3 N members. So this is the W matrix, and the other matrix, that is the H. So in the H, it is a P into M matrix, where as already mentioned, P and M values are already given. So P is the same one, that is the number of N members, and M is this one, like M is the different solute chemist composition. So this using that, what they have done is, initially they have given the values, like here if we see just, yeah. So just a second.
Okay, I think I get the idea. So I think that's why later on they also make some plots that are trying to say that some of the principal components correspond to certain, like the source. I think that's one thing that need to explain and comfort and validate. Scott, do you have any more comments?
No, it's just jumping in. It's an assumption, I think, of this non-negative matrix factorization that you have to specify a priori the number of sources. Is that correct? And then
Yes.
it figures out what the best mapping of histories to sources is, or is there a way that it's automating the estimation of that? You said it was sort of a priori less.
Yes, so they have, as it is mentioned here, that 2 known N member composition is mentioned. So as in this table S1. So here, what these are the inputs. So they have taken, initially this is a synthetic data set. So they have taken N member composition 1. So this is one N member composition. This is the second N member composition. And what they have done is they have generated a data set. So with 300 synthetic stream samples, from that N member composition, they are mixing in different proportion, and they are creating different stream samples. So ultimately, they are training the data set with that particular model. Then after the model is trained, they are putting the stream chemistry or the stream composition. They are giving that as an input for and the output are the N member composition and the different proportion in which they are mixed. So initially, they are giving in a synthetic data set. They are giving 2 N member composition, making different mixing them in different proportion, and giving a particular stream chemistry. So this is totally a synthetic data set which they are feeding to the as a training data, and from there then finally they are putting in the measured composition, and from there they're predicting.
But they're just assuming that there are 2 sources and that's it, and they're assuming that those the only 2 things, and they're just trying to partition their observed data into those 2 sources.
No, this is for the only training model. So in the training model, what they have taken this N members, but after when the prediction is being done, then no n member is being they're not feeding the n member composition into the data set. So in that case, this is not mentioned before the prediction. So this is an output in case of the predicting data. But
Sure, but when
while
you, I mean, just for this NMF algorithm, as far as I understand, you have to specify how many sources, like it'll break down V into two matrices, but P is specified, is it not, or is it somehow discovering that? That's what I don't understand.
No, P is being fed to the model, because initially they get the P by using PCA. So P is an input.
Okay, so there is some a priori knowledge. They know how many sources there are. Okay.
Yeah, I think I think that they although in the conclusion they say they don't, but it's not. I think the conclusion is that after they have some prior assumption to train the model, and then you don't need a prior assumption for the source. But for that model trained, then you do need this knowledge.
Sure, naturally, yeah. Okay, no, I was just curious. Thank you.
So Chen, how do you think? Yeah, go ahead.
So for that, here this natural samples are there because they are applying it in 3 different stream watershed, and there they are using the natural data. Also, not only natural data, what they're using is the prior knowledge what they have about the lithology, like earlier data they're comparing. So they are using their whole database. However, for training model, they are using the synthetic data. So the training is done based on a synthetic data model.
Okay, Chanel, how do you think they are mixing model? Because you're also working on the different mixing models for the cross composition, assuming different end members in the geologic history. So how do you evaluate their work for the mixing of the stream chemistry?
Maybe we can just also try to use this model to training the mixing composition of the content across. But for this paper, I think they just for this paper, I think they also just use the observations or the conceptual data to training. They did not use the natural samples to train, I think. Is that right? I think they did not use the natural samples to train the data. Is that right?
For the source.
Yeah.
So Wumi, do they have enough natural, I say, direct observations in the field for the training?
Because I think they just assumed the end members here.
Actually, for this, they as it is mentioned that already a large amount of work has been done on this area, and they have considerable amount of data regarding the chemistry. So it has been mentioned that, but however, even if we have a chemistry, we do not know the exact end member composition. So if we take, if we train, for training purpose, if we are assuming the end member composition, so that is done in normal cases, the earlier one that is meant they have mentioned. So just I'll go to that. So this one. So the traditional mixing model that assumes the end member chemistry, and this training is done on a natural data set. So however, in that case, what we have to assume is the end member chemistry. But this already, if we are assuming it, it might be wrong, because or there might be considerable error. So what they have done is, if we are taking a synthetic if we're taking 2 synthetic end members, then we have the whole control. We can mix and match in different ratios. So we can mix and we can create a database that is like 20,000 long, because we can mix that based on different proportions. So we can do the mixing in different, like to 20,000 different proportion, and in that case we'll have that amount of data, and we can increase that by bootstrapping methods and all. So we'll have a larger database and we'll have a control on how much mixing is done. So that is why I think they have used the like synthetic data, and based on that, they have, when they're predicting, then they're using the chemical data that have been measured. So they have considerable amount of actual data. They have the real data, but because if you're using the real data, then this n-member chemistry has to be assumed early. So therefore, using this particular machine learning method, they have like used the synthetic data to train the model, and as a result, during the prediction, they do not need the n-member chemistry, and they're using this. Actually, I think if we need to look into this particular NMF model, and then we can get an idea. It is actually just a second. It is actually a blind source separation model, and blind source separation model works in this way, as this way. So we need, I think we must, if we want to know more, we can read a little on the blind source separation. So I searched it, but I haven't read it in detail. So.
Okay, Wumi, could you turn to that figure you just showed earlier on?
Yes.
Let's say 1 minute ago. Yeah, Chuntao, my interpretation is that for Tangming's 2016 science work, I think what Tangming did was in the traditional mixing model to tell the evolution of the Earth's crust composition. And then for the PETAC work, they are not exactly using this machine learning mixing model, but they are using the two elemental ratio model, but they have tried, like say 16 elements, use 8 different element pairs for their EPSL paper. So actually this work, I think, is slightly one step further away from PETAC EPSL paper work, like in terms of the methodology. Yeah, probably something we should consider too. I think.
Yes.
I think it looks more reasonable for mixing model.
Yeah, for PETAC and Tangming, in their paper, both of them just consider or assume the n-member compositions of the continental crust by the silicate oxide contents. So, I think maybe in further work, maybe we could also use the same idea of this paper, but I do not take a look of the details of the paper. And I think we also could just with no assumption, without assumptions about the n-members, just like the unsupervised learning method, the concept of this method, we can just use the no n-member assumptions and use the raw data or the train data to get a better model, to get a mixing proportion of the composition of the continental crust, I think.
Okay. I think that's something you could look in the future. So Wumi, could you turn to the last part of your slides? I think page 14 of your PPT. It's not exactly related to what they're doing, but I'm curious that they're trying to say that Shell Hills and East River are carbon dioxide neutral, and then you have the Husband Brook that are basically is a carbon sink, right? Yes. So do they have any other evidence to support that? I suppose that if people have remote sensing images, etc., then people should be able to monitor the carbon dioxide emission as well as the sequestration globally. I don't know. I don't know. Well, I don't know anyone in this group.
They haven't used the remote sensing data, but however, they have compared it to the earlier work, and actually what they predicted, it is in line with the already predicted, already people have mentioned that their values are matching the earlier predicted ones. if we, because the earlier studies, they have only considered the CO2 weathering. So if we consider only the CO2 weathering, their results are matching with the earlier predicted results. How, like, for example, at
Yeah,
Hubbard group,
yeah, but for the previous methods, how did people make this calculation? Did people also use the similar approach as the way they do?
I'm not sure because I haven't, I
If,
like,
if it did the same hydro work, then yeah, I don't know. I don't know. Maybe Scott knows, because I think like how do hydrologists that really validate this is right? I mean, yeah, could any other approaches that could, let's say, validate it?
I'm gonna have to punt on this one. I don't know how you would determine if something is carbon neutral or not.
Yeah. I heard people make talks before that they use a different monitoring process. Like I said, for remote sensing, it's more like a really large scale, because for those guys, people work on the spectrals and then you can monitor on a daily change. And I think that's how that people track the carbon dioxide production of a country. Otherwise, how do you know that how many carbon dioxide that this country, this region ever emitted? I think there are also other ways that people did in the oil fields, in those like carbon intensive places, in the like the semi-natural system, not exactly perfect natural system, but also by monitoring, because people also have to figure out that, for example, in the carbon dioxide sequestration in the human projects, by injecting carbon dioxide in the pores as oil fields, that how much carbon has been stored there and whether it's leaking occur. I think there are monitoring processes that to monitor the process. I don't know. Maybe I could ask the speaker. Maybe he should know on Wednesday. Okay. Any other comments for this paper? Okay. Thanks again, Wumi, for your leading discussion. Thanks everybody for your participation. And on Wednesday, the speaker will give the talk, and probably he will talk a little bit more beyond this paper. So let's see what he's going to tell about his story. Maybe he will probably bring more information than that. Okay, have a good evening, have a good afternoon, and see you on Wednesday. Bye-bye.
Thank you. Thanks for the